Okay, let's talk about section 6, combinations of functions and composite functions. So what we should learn today is we're going to add, subtract, multiply, and divide functions. We're going to do composites of at least 2 functions. And we'll hopefully apply this to real-world problems. Okay? So first of all, some notation. When you add 2 functions together, we can write that like this. Function f plus function g of x. That's just the same thing as this notation here that we're used to. If we subtract 2 functions, we can write it like this, which is the notation we're used to. Multiplying 2 functions, we can write it like this. Dividing 2 functions, we can write it like this. Okay? So let's do an example then. Why don't you pause this one and try it. Here's function f, here's function g. I want you to add these 2 functions together and then evaluate it, what your value would be when x equals 3. So if we're going to add these 2 together, then obviously I like writing the notation like this. So it's f plus g of x, but that's the same thing as f of x plus g of x. Okay, so we're just going to add these 2 together. That's 2x plus 1 plus x squared plus 2x minus 1. Right? I just took f and added it with g. Now I can simplify by adding like terms. 2x and 2x make 4x, and 1 and negative 1 cancel. So this is the function. I could factor it and simplify it, but this is f plus g of x. Okay. Now, they want me to plug in 3. They want me to evaluate this when x is 3, so I'm just going to do it right from here, plug in 3. And this would be 3 squared plus 4 times 3, which gives me 9 plus 12, which gives me 21. So f plus g of 3 should be 21. You could plug in 3 right from the beginning and add f, so you could do f of 3 plus g of 3. You should get the same thing because addition is commutative. So that'd be 3 times 2 is 6 plus 1 is 7. And then 3 squared is 9 plus 6 minus 1 gives you 14. 14 plus 7 gives you 21. Either way, you're going to get 21. But this is the notation I want you to show me, if you could. All right, next we're going to do compositions of functions. So this is our notation. It's f of g of x, and you evaluate g of x first and then put it into f of x. Okay, so this is just a mapping diagram. It says you take x and you would do some function g to it, then you do some function f to it, and you get the composition. And the same notation you could use as f of g of x right here. That's the little composite symbol, that little circle. So let's try an example. All right, so this wants us to do this composition. It wants us to do f of g of x. So we're going to take x, we're going to stick it into g, then we're going to take g and stick it into f. So f of g of x would be g of x, which is the 4 minus x squared, stuck into the domain of f of x. So if I want to write this out step by step, I'll do, this is f of now g of x, which g of x is 4 minus x squared. So I need to plug this into the domain so it goes in for this x right here. So it would be 4 minus x squared plus 2. Right, I just took this and stuck it in right in here for this x. And then I can simplify. This is negative x squared plus 6. This is my f of g of x. This is my composition right here. Let's try b then now. So with b, we want to do g of f of x. This is the other way around. We want to take x, stick it into the domain of f, which gives us this. And then we want to take that and stick it into the domain of g. So we're going to end up with 4 minus this squared. So all we did was take x, we stuck it in the domain of f, and we got x plus 2. We took that then and stuck it into the domain of g of x, and we get this. Okay, now we can simplify from here, which will give us 4 minus, in parentheses, this would be x squared plus 4x plus 4. Then I can subtract all these. So I'm going to distribute the negative sign to every term. This gives me 4 minus x squared minus 4x minus 4. The 4 and the negative 4 cancel. And I ended up with negative x squared minus 4x. This is my g of f of x. Simplified. That's what I'm looking for. Let's try one more then. Let's try c. C wants us to do g of f of, and now it gives us an actual number here. So to do that, I would take negative 2 down. I'm going to rewrite this. So g of f of negative 2 can be rewritten like this. G of f of negative 2. This notation is a little easier for some students because it's saying you take negative 2, you stick it in the domain of f, you take that number, then stick it into g. So that would be negative 2 stuck into f gives you negative 2 plus 2, which is 0. So we really want g of 0. And g of 0, if you plug in 0, you get 4. So the answer for this is just 4. So I can say g of f of negative 2 is just 4. All right, let's just try some application then. Here's an example with bacteria count. Let's say that n represents this function right here represents the number of bacteria after some temperature. So as the temperature increases, the bacteria increases. But if the temperature gets too hot, the number of bacteria will obviously start to die off. So this function, we could, if we have some data, we could do some quadratic regression and model the number of bacteria in a petri dish, for example, in comparison to temperature, in relation to temperature. We'd have this function. Okay. Let's have another function then where t is the temperature in terms of time. So if we make a relationship between how hot the petri dish gets after some amount of time, we have this function, let's say. As we increase the time the temperature is rising, let's say it's a linear model on some Bunsen burner. Okay, so then we can answer some questions. We can find the composition of these two functions, and we can interpret its meaning. We can find the time when the bacteria reaches 2,000. So why don't you guys try this one real quick and see once if you can answer these two questions. All right, so if we want to find the composition of this, let me just get this out of the way so I can do some work here. The time in terms of t is this function. I'm going to stick that into the domain of this function. So my n of t, I'm going to take this function right here and stick it in right for the domain, right there and right there. So I'm going to have 20 times this function squared minus 80 times this function right here plus 500. So take a second to see what I did. What I did is I took this function right here and I just put it into the domain of this function n. So I put it in here. If you want me to show more work, I guess I could do that and say this is going to be n of the next step right here. If I want to put that in there, would be n of this function 4t plus 2. So what I'm doing is taking this and sticking it into the domain of this function, in which case it goes in here and it goes in here. And you get this function. All right. So now I can simplify this function, n of t equals, and you can FOIL this all out. You guys, I'm sure, can handle this. I'll do it real quick. 20 times 16t squared plus 16t plus 4 minus 320t minus 160 plus 500. All right, if I simplify this then, I get, sorry, I need to close these parentheses. 320t squared plus 320t plus 80 minus 480t. Oh, wait, I'm sorry. These are like terms right here. Minus 320t plus 340. Now I can add these like terms. Actually, these like terms cancel. And 80 plus 340. So I end up with 320t squared plus 410. 420. All right, so this is our composite function now. And what this represents, the meaning of this function, is the number of bacteria after some time. Because what we originally stick in is time into this time function, and what we end up getting out of the function is number of bacteria. So what this composite function gives us is after how much time, how much bacteria is there per unit of time, right? So we stick in time, and we're going to get out the number of bacteria. That's what this function is going to model for us. which could be very helpful. The next question just wanted us to find the number of time when the bacteria reaches 2,000, in which case we plug in 2,000 for the range, and we solve for the amount of time, right here. Different ways to do this. Obviously, you could subtract 2,000 from both sides, use the quadratic formula. I'm going to graph this, just because I think this will be quickest. Yeah, actually, better than the calculator, I didn't realize it wasn't a variable here. Better yet, let's subtract 420 from both sides, and then we can solve for t. Divide both sides by 320. Let's see. This gives us 2,000 minus 420 is 1,580. Okay, so this gives you 1,580. Then divide both sides by 320. This gives you 4.9375 equals t squared. Square root both sides, and this gives you the time is 2.22. Approximately. I think that was in minutes. Let me double check this real quick. Foods and refrigerated by temperature, foods given by in hours. So it's 2.2 hours. After 2.2 hours, there will be 2,000 bacteria in the dish. Okay. I know this application doesn't seem like something that you'll ever use again, but if you are a scientist studying the growth of bacteria, for example, maybe you're studying the evolution of bacteria in different solution levels, I don't know. You could use this math again someday. All right, hope this helps.